Welcome to this lecture on some special matrices and their properties. This may not be an exhaustive discussion, but it gives the fundamental knowledge to approach higher concepts in linear algebra. So first, let us talk about invertible matrices, and after that, we will see what are near singular matrices. A matrix is invertible basically if it is square with a determinant not equal to 0. If A is an invertible n by n matrix, then it will be a full rank and the vectors of A are linearly independent. 0 cannot be an eigenvalue of A, and the linear system Ax is equal to B has a unique solution for all B in the Rn space. So this is a very powerful statement, and there is one matrix which we shall call a nearly singular matrix or a near singular matrix or an ill-conditioned matrix. Now such a matrix will have a determinant very close to 0 and whose inverse is unreliable. The extent of ill-conditioning of a linear system of equations is determined by the condition number of the matrix. So linear system of equations require analysis for stability of solutions, and that depends upon the condition number. That was already discussed in the previous lecture. Now let us broadly classify today's discussion into three parts. One is the important real square matrices. Of course, this is not an exhaustive list. And then we'll follow this up with complex square matrices and some of their properties. Now, among the real square matrices, the first one is a symmetric matrix. And a symmetric matrix can be recognized by the rule that A is equal to A transpose. Now, a symmetric matrix visually appears something like this. It is a square matrix that can be flipped across the diagonal without changing the elements. So, it's an easily recognizable matrix. So the rule is A is equal to A transpose. Symmetric matrices are of very great importance in the understanding of quadratic forms. Now when we talk about the eigenvalues of a symmetric matrix, they can be proved to be real. That means the eigenvalues of a real symmetric matrix fall on the real line. Eigenvectors corresponding to distinct eigenvalues are mutually perpendicular, which we shall discuss in a later lecture. As already mentioned, symmetric matrices are critical in the study of quadratic forms. And whenever we have a cloud of points in multivariate data, in order to understand the structure, we require quadratic forms, and quadratic forms involve symmetric matrices for analysis. Then comes a skew symmetric matrix, which requires that the rule A is equal to minus A transpose be satisfied. So here we have an example of a matrix A, as you can see, with 0 diagonal elements. And then it's very important to understand that in a skew symmetric matrix, there is a sort of symmetry about the diagonal, but the elements have to be negatives of each other. So we first write A, find its transpose, negate all the elements, and check if A is equal to minus A transpose. So this makes it a test for checking skew symmetry. Now when you talk about the eigenvalues of a skew symmetric matrix, they're either 0 or purely imaginary, which means that the eigenvalues of a skew symmetric matrix lie along the imaginary axis. It is always a singular matrix and hence not invertible. Then comes a very important matrix called the orthogonal matrix. It should be square and should satisfy the rule A into A transpose is equal to A transpose A is equal to I. What is very important for orthogonal matrices? All the row vectors as well as the column vectors should be orthonormal, which means they must not only be mutually orthogonal, but they must be of unit length, row-wise or column-wise. This is an example of an orthogonal matrix. When we check the determinant, it will be either +1 or -1. And a very important statement to be made is an orthogonal matrix of determinant +1 is called a rotation matrix. Since in an orthogonal matrix, we will find the determinant is either +1 or -1, it is non-singular, therefore invertible, and it follows from the definition A into A transpose is equal to I, that A inverse is nothing but A transpose. So it's one of the easiest way to find out the inverse of an orthogonal matrix. Now when we determine the eigenvalues, we find that the eigenvalues of an orthogonal matrix can be real or complex, but they must be of unit modulus. That means they lie on a unit circle. So having seen these three important real matrices, there are three very important observations that A plus A transpose and A into A transpose are both symmetric matrices. A minus A transpose is skew symmetric matrix, and any square matrix can be decomposed into two parts, a symmetric part and a skew symmetric part by the rule A plus A transpose by 2 plus A minus A transpose by 2. Now let us come to complex square matrices. Analogous to the symmetric, skew symmetric and orthogonal matrices, we have in the complex case the Hermitian, skew Hermitian and the unitary matrices. The only thing is the elements in this case will be complex numbers. So let us talk about a Hermitian matrix. A is called Hermitian when A is equal to A star, where A star comprises of conjugation followed by transposition. So this is an example A where it is equal to A conjugate transpose. So one can easily check. First find the conjugate and then take the transpose. It tallies with the given matrix. Now when you find the eigenvalues of Hermitian matrix, you'll find they will lie on the real axis, which means there is some similarity in the behavior of eigenvalues of a symmetric matrix and a Hermitian matrix. Then comes the skew Hermitian matrix, which should satisfy the rule A is equal to minus A star, that is A is equal to minus A conjugate transpose, and this is an example for a skew Hermitian matrix. Observe in a skew Hermitian matrix, the diagonal elements are either 0 or purely imaginary quantities. The eigenvalues of a skew Hermitian matrix lie on the imaginary axis, which means they will be either 0 or purely imaginary numbers. Then comes the unitary matrix. A square matrix is called unitary if it satisfies the rule A into A star is equal to A star into A is equal to I. And here is an example of a unitary matrix, U. So we first compute U star. Of course, U star itself comes through conjugation followed by transposition. Then we multiply U with U star and we find we should get I. So U into U star is equal to I, which makes U unitary. And the eigenvalues of unitary matrix lie on a unit circle, which is again the property that orthogonal matrices have. So as far as eigenvalues are concerned, there is similarity in behavior of symmetric and Hermitian, skew symmetric and skew Hermitian, orthogonal and unitary matrices. Now, just in the case of real matrices, we also have some statements to make about complex square matrices. A plus A star and A into A star will both be Hermitian. A minus A star is always skew Hermitian. And a complex square matrix can be decomposed into Hermitian and skew Hermitian parts as A plus A star by 2 plus A minus A star by 2. We'll close this discussion with a small definition of positive definite matrices, which are very, very important in the context of function optimization. A symmetric matrix A is called positive definite if the scalar product X transpose into A into X returns a positive number. for any vector x in Rn which is a non-zero vector. There is an alternative definition. Is a symmetric matrix A with real entries is called positive definite if all its eigenvalues are positive. This is an example of a positive definite matrix. So you can take any vector in 3 dimensions, x, which is non-zero, and perform the multiplication x transpose Ax, you will find that it returns a positive value. So this is an example of positive definite matrix, about which we can discuss in quadratic forms later. But positive definite matrices play an important role in some important matrix decomposition procedures like the Cholesky decomposition and in multivariate minimization problems.